Right, okay. Good evening, Year 11. Welcome to your physics last live revision session. So this is for AQA Trilogy GCSE Physics. The first hour this evening is going to be for Trilogy students, okay? The second part, the last part, will be for Set 1 students at Horizon, or if you go to another school, you may call it Separate Science, GCSE Physics, you may call it Triple Science at some places, but we will tell you when we switch between doing the Trilogy of Science and the Separate Science, okay? My name is Mr. Schuller. I'm the person that's been reading all your comments for the past 5 sessions, and I'll be taking you through your first topic based on forces, and then Mr. Cattrall is going to take you through waves and electromagnets as we go through, okay? Now, in the stuff on all the forces stuff, we're going to be talking about, I will put higher tier only at the top, so you'll know whether it's something for higher tier only students or not, okay? So you'll notice at the top, for example, if you look at this one, you'll notice that it'll say HT only on that one, okay? So we're going to start off by looking at vectors and scalars. Now, this is something that you will have touched on maybe in maths in the past, but you do need to know the difference between a vector quantity and a scalar quantity. Now, the biggest difference between them is what they have in terms of their a direction or not. So vectors are things that have got a size, or what we may call a magnitude, and direction. Okay, whereas a scalar has a size or magnitude only. So we must remember anything that is a vector measurement that we're using will always have a size and will always have a direction. So when we think about examples of vectors and scalars, the first one that you can talk about straight away is force. Okay, forces are vectors because they always have a size and a direction. Velocity is the speed of an object in a given direction. Displacement, the one that people always forget about, displacement is the distance an object has travelled in a given direction. Okay, as soon as you put that direction part in there, you're talking about. So I'm just going to see if I can focus this camera a little bit more. Year 11. There we go, so a bit better. When we're talking about scalars, we might be thinking about things such as time, temperature, distance, speed, because these are things that have just got an amount or a quantity or a size only. Okay, so make sure you know the difference between both of those. Now, I want to pick up on forces because, as you know, Spec 5 in physics is all about forces. And for this one, what you need to be able to look at are examples of contact and non-contact forces. Now, in terms of these, there are some that you do need to know, okay? And it's something actually, it's quite straightforward. You don't need to overcomplicate it. You don't need to start thinking of massive, really big, over-the-top examples. Really simple things, such as, for contact, friction. In order for an object to experience a friction force, it needs to be in direct contact with another object, okay? Tension. In order to feel a tension force, you need two objects to come into contact with each other, okay? So thinking about things, when you think about the required practical for waves, when you're trying to work out the speed of waves in a solid and using a piece of string, the string is held tight via a tension force. Air resistance. This is one that people get confused about because people think, well, air resistance, how is that a contact force? Well, actually, remember, the air particles are directly in contact with you. When you are running and you feel the wind on your face, that is an example of air resistance. And the air particles are directly hitting your body. And that is why we class it as a contact force. Examples of non-contact, the biggest one is gravity. In order to experience a force of gravity or a gravitational force, you do not need to be in contact with an object. For example, if you jump up, you immediately are pulled straight back down to the ground by the force of gravity. And when you're in the air, you are not touching anything at all. Okay? Electrostatic force. So when we start thinking about things such as force involved with lightning, when you start thinking about force, particularly I was thinking, for example, I was using ionic bonding, okay? The electrostatic force between two ions is there even if the ions are not directly in contact with each other. Okay, so we class it as non-contact. So make sure you are able to recognise the difference between both of those. Now, if you've been in school over the past couple of days, you will have done some work either with the maths department or with, I think it was business and P and other departments the other day. And if you came to the booster we put on today, we did a little bit of work on this as well. Okay, from another school you may not have done recently. This is all about being able to represent a force using a scaled diagram. Now, those of you that I've done some work with today, you know we talked about scaled vector diagrams. At the moment, we're not going to touch on that. That's going to come a little bit later on. All we're going to focus on at the moment, sorry guys, that camera's a little bit, no, just going to get a bit clearer. Should be a little bit better. All we're thinking about using is just using an arrow to represent a vector. Okay, I'll use a representative force, sorry. So, for example, we could pretend that 1 centimetre is equal to 1 Newton. All right, so 1 centimetre is equal to 1 Newton. So, to represent a force of 10 Newtons, I've drawn a line 10 centimetres long. Okay, and obviously, because it is a vector and it's a force, it needs a direction. So, I'll put an arrowhead on. I could say the force is to the right. I could use compass bearings and say it is east as well, but it's important I'm giving that direction as well to it. I could draw, for example, we could say there's a force acting downwards with a size of, let's say, 20 newtons. And you'll notice now, and I'll put it up there, that 20 newtons doesn't quite fit on my page. So I can't just use 1 centimetre equals 1 Newton. I need to come up with some form of different scale. So what I might do is I might say, okay, well, 1 centimetre equals 2 newtons. So we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so this time 1 centimetre has equaled 2 newtons. So this is 20 Newton force. I'm going to put downwards. I might put south. And I'll just put there 1 centimetre equals 1 Newton. You could be given for example, a scale to use. So the question may have some information already there. And you may be asked, so for example, it may be something like, let's have a look. I'll show you later. Examples, they may be given some information already on the question, and you could be expected to work out a scale from that. Or you could be asked to come up with your own scale. So like I've just decided that, you could be asked to just decide your own as well. And that's absolutely fine, okay? But just check the question first before you make a start. You don't want to make any mistakes as you go through, okay? Now I want to pick up on another force. I want to look at weight and mass. We're really bad for this in everyday lives. People always say, oh, okay, I've lost weight. That's really good. I'm on Slimming World. I've lost weight. Or people say, oh, I'm really sad. I've put weight on. But actually, we don't put weight on in that point, because we're actually talking about, in our case, we're talking about mass. Mass is basically how much stuff or how much of you there is, okay? It's a measure of how much matter there is, and it is always measured in kilograms, okay? Some people say I've put weight on or I've lost weight. Actually, what they mean is I've lost mass or I've put mass on, because weight is a measure of how much force is pulling an object down to earth because of gravity, okay? So if we've got a, I don't know, I'm just going to use an idea of a box, because those of you I teach know my drawings are absolutely poor. Weight of that box would be how much force is pulling that down to earth, okay, because of gravity. So it could be being pulled down like that. It could be just sat, okay. It could just be sat on the ground like that. Doesn't matter. That will still have a weight because it's been pulled down to the ground and kept down at the ground. It's not floating away. When you're in school, you don't just sit in a science lesson and just float off and hit your head on the ceiling. You are kept down to earth, and that a measure of how much force that is your weight. Is your weight. And because weight is a force, it is measured in newtons, and we use a capital N. Do not put lowercase, it has to be capital, okay? So weight is a measure of how much force is pulling an object down to earth because of gravity. Now, there is a possibility, if you've done this if you've done this at Key Stage 3, Year 7, Year 8, we talk about weight of people on other planets and other stuff like that. Your mass in physics, unless it suggests otherwise, does not change. Your mass will always stay the same. Okay? Unless it says unless it tells you that something has gained mass or lost mass, it will stay the same. However, your weight can change, because the amount of weight there is dependent on the strength of gravity. Okay? Or you may call it the gravitational field strength. So depending on what planet you're on, depending on how much gravity there is, depends on how much weight there is. So if somebody says to you, I need to lose weight, tell them to go to the moon and they will instantly have lost some weight. Okay? If you want to put weight, if someone's put weight on, ask them if they've been to Jupiter, because that's the only way actually you can change their weight. A magic triangle for you. Okay, now you may have not used magic triangles at your school if you're not at Horizon. You may have done it the old school way by rearranging an equation or changing the subject of a formula. Now, when we get to uniform acceleration, so v squared, u squared, 2as, all of that, I will go into that math skill, is equal to the mass multiplied by the gravitational field strength. And we cover up whatever we are looking for. So if you're asked to work out weight, cover it up and it's mass times gravity. If you're asked to work out mass, for example, cover it up and it will be weight divided by gravity. So I've got a box and it has a weight, not a mass. You'll notice, you know it's a weight because it has got something in newtons. It's got a weight of 1,462 newtons. And you'll notice I've been given a little number down there. Now, you will be, it says on the specification, I've just checked, if you need the gravitational field strength for a weight, mass and gravity question, you will be provided with this value, and they made that very clear on the specification. If in doubt though, if for some reason they put that in just to basically terrorize a little bit, always use 9.8. Okay, so if you do need a reference value, you can go to 9.8, but the specification is clear that you are given that value. All right, so we've got a value of 9.8, we've got that. The question could say, what is the mass in kilograms? All right, so I'm going to go to my triangle, cover up M, and the mass is equal to the weight divided by the gravitational field strength. Okay, the weight is 1,462 newtons. 1,462 newtons. The gravitational field strength is 9.8. So pop that into, I'll get your calculator there. You may be able to see the numbers, you may not do. I apologise if you can't see. It's 1,462 divided by 9.8. So I'll just bring that a little bit closer so you can see. It's 1,462. Literally, I'm working my screen at the moment, it's a mirror image, so I'm trying to guess where to position it. Get your equals, change that by pressing SD there, SD to a decimal, and we get 149.18. Okay, we'll round it to one decimal place, it's 149.2. And because it's an equation, and in an exam they may not give you the units to put on, it depends on what tier you sit in and depends on the question. I've not been given the units, so I'm going to include kg for kilograms, and that's how you would score your full set of marks on a question like that. Okay, centre of mass. This is chucked in random a little bit to gravity. Now this is all based on the idea. That camera's a little bit blurry again. Sorry guys, this camera's a little bit blurry on the edge. Okay, sorry, I'll just try and focus it a little bit for you. That's a little bit better. Okay, so this is based on the idea that if you've got an object and it has base has mass, it's looking at things toppling over. So I've got a really simple diagram of a bus. Okay, now excluding in the question, centre of mass. I've marked that by putting a pencil down. I'm going to put a big fat black dot there so you see it clearer. Now, centre of mass is acting in the centre. And if I drew a line from the centre of mass straight down to the ground, you'll notice that the centre of mass line is outside of the edges of the object. In our case, it's outside the edge of the wheel. So that bus would topple over, okay? If it was on something, it was on a camber road, a twisted road like that object would topple over in that way. However, this one, if we look, the centre of mass, we follow the line down straight with the ruler, is inside of the object, okay? It's inside of the object. So you'll notice now, because of that, it's inside of the wheels, so that object would not topple over, it would stay upright. There are questions, past question I've seen is as well as using buses. There's questions where I'm just getting a nice quick pencil, let's use a nice pink one, where it's a gentleman or a lady, I think it's a gentleman, but it could be a lady, on a set of ladders. Okay, and they're climbing up. They climb up to the top there. So notice the top of a ladder overshoots the sort of support bit there. And the question is, why won't they? What would happen? Now, you've got to think about centre of mass. Centre of mass is here, okay? We're sort of talking in this line here, so I'm bang in the middle. And if you notice, the centre of mass falls inside the ladder frame. So the gentleman or lady wouldn't tip over. If the ladder carried on and on and on and on up there, and the centre of mass came here, for example, then it would topple over and someone would get injured. But because it is the inside bit there, they are not going to fall off. And the same with the bus will not topple over. Okay, if you've just joined us, this is all foundation and higher tier knowledge. It could be on the trilogy paper, it could be on the separates or triple paper as well. All right. Now, resultant forces. Resultant force is a sum of all the forces acting on an object. Okay, so resultant force is the sum of all the forces acting on an object. In this example here, okay, we've got a box. Now, it's being pushed with a force of 20 newtons. Okay, so we've got a push force of 20 newtons. Sorry, that camera's still really blurred on that one side. I do apologise, year 11. If some reason it decides it wants to be blurry on one side, which is a little bit annoying. Let's have a look. That's a bit better, I think. Yeah, okay, so we'll push forwards with a force of 20 newtons. So somebody somewhere is pushing this box with a force of 20 newtons. The box has got a resistive force. So in our case, it's probably going to be friction with the ground, a resistive force of 10 newtons. The resultant force, like I've said, is the sum of all the forces acting on an object. So what we do when we work out resultant force is we subtract them. Okay, so take them away. So 20 minus 10 equals 10 newtons. So that's resultant force. What have we missed? We missed a direction. And remember, forces are vectors, so they need a magnitude or size, and they need a direction. So what we need to do is we need to work out which way it's going to go, and it will go in the direction of the biggest force, okay, which is to the right. So I could put to the right, I could draw an arrow. You could put forwards. If it's got someone pushing it that way, it's got a person there and their hands on it. Don't know why they've only got a head and one arm. If you're doing it that way, then it will be that way. But you've got to give some form of indication that you know which way that force is going. Okay. Now, this is also, the next bit then is to work out, what if the resultant force is 0? What about if we've got a moving object? What about if we've got a car, for example? Now, though, once again, my beautiful drawings here, please excuse them. Let's say we've got a Land Rover, because it's easy to draw, and it's got eyes for wheels. Window there, exhaust, me smiling, exhaust there. Let's say we've got, I don't know, I'm going to use 100, just a round number, 100 newtons of push force, of driving force on the engine. So 100 newtons of driving or push force. In total, because I'm going to use different pen, we've got 50 newtons of friction from between the tyres and the road, and I've got 50 newtons of air resistance. So my resultant force for this, okay, we need to put these two into one force. So 50 add 50 is 100. So I'm going to cross them out. So in total, it's 100 newtons. Take them away. Now, it doesn't take a genius to work out the 100 minus 100 No, it doesn't equal N. That should say 0 newtons. So the resultant force is 0. Okay. Now the key bit here, and if you get this in the exam, guys, you need to check your blurb in your question. If the object, it will tell you whether the object is moving or if the object is stationary. Okay. Because if it's moving and the resultant force is 0, it's very different to if the resultant force is 0 and it is stood still. Okay, so you need to make sure you read your blurb on that. And this leads me on to my next point. We can summarise the resultant force and its effect in a nice little table. And this is actually something called Newton's first law. So this does coincide with something later on. Because I'll talk about second and third law, but I won't talk about first because we've covered it here and I don't want to do the same thing twice. So if we've got an object that is stationary, so something stood still, and you work out the resultant force, it comes out at 0, that particular object will stay still. It will not move. If you've got a stationary object and the resultant force is not 0, so for example, the amount of push force from the engine of a car is greater than the resistive force, so you get it, basically take away, get a number, the object will accelerate or speed up, okay? Because you're going from a standing still and you're getting faster. If you've got a scenario like from my dodgy Land Rover before, and you take the numbers away and the resultant force is 0 and it's already moving, it will stay at a constant speed. Because for all of the force you're putting in to push the object forwards, the same amount of force is trying to resist and stop it. So they cancel out and it becomes 0 and it stays at a constant speed. If you've got a moving object and you take the numbers away and it's anything other than 0, it's either going to accelerate, so speed up, or it's going to decelerate, which is slow down. You do need to make sure you know those, guys, because what they will do is they may ask you to apply that learning to one context or another context. It all depends with forces. There are multiple opportunities for that in there. Now, the next bit, I will warn you now, is higher tier only, okay? And this is using scaled vector diagrams to calculate resultant force. And I'll say that again, this is higher tier only. So no on previous ones, you wanted to know which bit's higher tier only and which bit's a foundation and higher. And this is anything with HT at the top is higher tier only. And I pre-prepared a question just to make it a little bit easier. I'll read it to you in case you can't see it. The two forces act on an object. One force is 5 newtons to the right, and the other force is 12 newtons upwards. Draw a scale diagram to find the magnitude and direction of the resultant force. Now, you'll notice the key word here, I'm going to crack out a yellow pen for this, scale. Nowhere on here does it tell me a scale, so I need to make my own. Okay, so what I'm going to do is I'm going to knock out my ruler that you'll get in the exam. I'm going to do this in pencil just because it's a little bit easier, because felt tip pens are a little bit too, they've got fat nibs, it's hard to see. So what I'm going to do, first of all, I'm going to do my horizontal force to the right, and I'm going to use a scale of 1 centimetre equals 1 newton. Now, a little bit of advice, just to cover you back in the exam, write down the scale you're using, okay, because then the examiner knows exactly what you're doing. You don't want to leave anything to chance, so for the sake of doing that, it's worth it. So I'm going to do my 5 centimetre line there for my 5 newton force horizontal, like that. I'm then going to do a 12 centimetre line, so it's doing 5 centimetres to the right, then 12 newtons upwards. Okay, now it really annoying, really annoying, is going to go into the question. So we'll work with it. In fact, no, let me do another one here. Sorry, guys, because I don't want to make a mess of that. So let me go here again. Sorry. 5 centimetres across, and then we're going to go 12 newtons upwards. I should have checked my scale there. Naughty, naughty, Mr. Schuller. So I've been asked to find the resultant force. So what I do, and because they're at right angles to each other, okay, because in our case, the question's not told me, but I know they are, and the question would tell you, unless it says otherwise. What I need to do, and I will do this in felt tip, is I need to draw a line to connect these two together, and that is the resultant force, okay? So from there to there, and we're going that way and that way, so the resultant force will be pointing that way. The next job now is to use the scale that I've come up with. So 1 centimetre is 1 Newton. I'm going to measure this line because it's a scale diagram. So I'm going to put that bit on 0, and it comes out, comes out at 13 newtons. Okay, so my resultant force, losing a pen, is 13 newtons. But what am I missing? I'm missing a direction. Okay, and because it's a force, it needs a size and a direction. Now, there's multiple ways here we can go, multiple things you can provide information depending on what your exam asks you for. You could go with a bearing, so you could say northeast, you could say upwards, but you could be asked to provide the angle. Okay, now what we're looking for here is looking for the angle there, because you could say it's 13 newtons at so many degrees to the horizontal. So for us, crack out the protractor, and it comes out 108. So it's actually 13 newtons, 13 at 108 degrees to the horizontal. You could, if you wanted to, measure this angle, and it could be at so many degrees from the vertical. Just check your question, and it depends on what they're looking for from that one, okay? And there are some different avenues you can explore dependent on the question. Just point out now at the moment, if you do have any questions, we haven't got live chat on tonight, Year 11, but we are on Twitter. Our hashtag, our Twitter name is at HCC_depth of sight. Drop us a tweet or use a hashtag AskTeamSci. All right. Now, I'm multitasking a little bit at the moment, so I'm not sat with my laptop in the side room at the moment. So I'm just watching everything as we go through. So I may have to come to your questions towards the end of this. So please just write them down, scribble them down somewhere, and I will answer them as we go through. So that's if your forces are at a right angle. Your forces may not be at a right angle. For example, something like this. These forces are not at right angles because I've been given the angle there. So I've got, and I know this is a scale diagram because my questions told me. You can't see it here, I pre-planned, but it would tell you in your question that this is to scale. So I've been asked to work out and calculate for this one, once again, the resultant force. For this one, I can't just crack out a triangle because it's not at a right angle. So what I need to do is I need to use another strategy. And what I'm going to create is a parallelogram. So I'm going to measure this line first here because it's to scale. And it's 10 centimetres and it's 10 newtons. Brilliant. It's almost like I made this question up. So 1 centimetre, and I'm just going to put it here so I don't forget, is 1 Newton. I'm going to measure a line here that is also 10 centimetres. I'm going to do that to my ruler upside down because if you've ever drawn with felt tip pens on a ruler, you know it causes absolute carnage and smudges everywhere unless you turn your ruler upside down. If you didn't know that, top tip. Next one, measure this line. This line is 5 centimetres. Okay, tiny bit over, but we're going to pretend it's 5. So I'm going to draw a line 5 centimetres here. Now you'll notice, that's part of the way, you'll notice here, look, surprise, surprise, that matches up and it's 5 centimetres. So I'm just going to join this up with that. We've now got a parallelogram. My resultant force is now going to be, she's purple, is now going to be this way. So from corner to corner. And it needs a direction. So I'm going to put an arrow on it. So we could, once again, we could say it's going northeast. We can measure an angle, which I'll go to in a minute. The next bit that we need to do is we need to work out the size of it. We've only drawn an arrow on, that's only half of the story. So we need to measure this line. It comes out, if we're being technical, which we should do really, it's about 13.7. So that line is 13.7 0.7 centimetres, and our scale is 1 centimetre to 1 Newton, so the resultant force is 13.7 newtons. Okay. Now, measuring the angle, I could go from the horizontal again. So 10, 20, so it is 20 degrees to his horizontal, so that's my direction. I could do it to my vertical as well. You know, I could do it this way, so I could put my protractor that way and count backwards. It's absolutely fine. I wouldn't overcomplicate it. Let's face it, folks, you've got enough on your plate with this as it is, rather than overcomplicating everything and making it really difficult. We're still on higher tier because we've got a HT. We could be asked to go the other way. So instead of taking two forces and resolving them into a single force, you could be asked to resolve a single force into two separate ones. Okay, so for this one, it says resolve a single force of 100 newtons at 30 degrees to the horizontal into two components acting at right angles. Now, the critical bit for us there is it's a single force. It's 30 degrees horizontal, and they're acting at right angles. So we're taking one force and we're going to turn it into two separate ones. Okay, so it's actually the opposite of what we've just done. So what we're going to do, first of all, is I'm going to draw horizontal. I need to draw horizontal because that's where I'm going to start from. Not doing pencil, actually. Sorry, you're just watching me twiddle a ruler around. Let me just take these sheets out as well because it's getting a little bit cramped on here. That's better. So I'm going to start off by drawing horizontal. Now, it looks faint. There's a reason why it's faint, and you'll see why in a moment. That camera looks a little bit blurry again. Sorry, guys. I keep losing focus for some reason. So it looks like you're watching it, and it's not very focused. Sorry about that. There we go. That's a lot better. Yeah. Sorry about it. We're using a webcam at the moment. It's a manual focus. So for some reason, it just decides it doesn't want to keep focusing, gets the face on. So, horizontal line. I'm now going to measure 30 degrees from my horizontal line. Now, 0, and I'm going to hold this up so you can see because it's actually surprising when a number of students who can't use a protractor. So I'll try and hold it close so you can see. Hang on, sorry, I'm on a mirror image again. Wait there. It's no spatial awareness. So 0 is here, 10, 20, 30. I'm using the inside scale. I'm not going to go all the way around to 30 down there because I'm measuring from this line. And that's 10, that's 20, that is 30. So pop it on here, 30. Mark it on. So my line now is going to be 30 degrees. And that's a 30-degree angle now, so it's to scale. It's a scale diagram. Now, I've been told that the force is 100 newtons, and it's a scale diagram. So I need to knock out my own scale again. And let's go for it. Let's just use, is it going to fit? Yeah, beautiful. 1 centimetre equals 1 newton. That's your fail-safe. If you don't know what you're on about, and you get a bit nervous, and you get a bit clammy, and a bit panicky, just go for 1 centimetre equals 1 newton. Unless, obviously, it's not going to fit on your page because your force is 1,000 newtons. Don't use it then because you'll end up going over the exam table and carrying on down onto the floor. So check it's appropriate first. So 10. Once again, knocking my ruler sideways just so I don't make any squiggles and make a mess of this glorious picture. There we go. So that now is to scale. I now need to resolve it into two components. So I'm now going to once again get my pencil and do a faint line going on. And actually what I'm doing is I'm actually making an axis, if you'll notice. I'm making two axes like that. Hopefully it's at 90 degrees. Let's have a look. Yeah, bang on 90 degrees there. So okay. Now I've done my scaled line, what I can do is I'm going to go from here. Pen. What colour? Choose red. So I'm going to go from here and I'm going to draw a line down to the vertical component, to the vertical, the horizontal line, so horizontal line. I'm then going to do the same across to the vertical on that side. Okay. I'm then going to use another colour to help split this up a little bit. Choose bright green again. And I'm going to now draw in full. I mean, obviously you haven't got felt tip pens, I get that. So you use just biro or pencil or a highlighter, whatever. There's no set code. I'm going to make this line up to there solid. That there is my horizontal force. I'm going to do the same here. I'm going to go from there all the way down onto that one. That one is my vertical force. So I've taken this force here and I've resolved it into two separate components at right angles. Now, I'm just going to quickly label this up in case you want to play this back. Don't forget that's at 30 degrees because the question tells us it's at 30. So I've now got my two arrows, but I've not got a size. So I'm going to go back to my scale and I'm going to measure this line. So from there, I've overshot a bit. It comes out at 8 points, roughly round about 8.2 centimetres. So it's going to be 8.2 newtons, straight conversion. This one, I'm going to do the same again. So horizontal cross, we're looking at about 5.4-ish centimetres, roughly. I'm going to do an approximate sign just because I'm not too sure. That's what you do if it's an approximate answer, and I'm not 100% with this. So that equals 5.4 newtons. So my horizontal component is that big. My vertical component is that big. The resultant force is, hang on, actually, what I've just realised, I've done a bit of a mistake here. I'm really sorry. I've just realised this is 100 newtons. I'm going to change it to 10. Sorry, that should say 10. So now, try again. So now that's right. So my resultant force is 10 newtons, and then these are those two on there. Sorry if you're watching that and you couldn't comment to take comments off, getting really cross at me. It's been a long day. If you've been in year 11 today, you'll know what I'm talking about. If you've been in school, it's been a bit of a beast. So what you've done is taken that, you've resolved it. All right. This ends the higher tier section. The next bit now is foundation and higher. Okay, so all that I've just gone through and spent a lot of time doing is higher tier only. This is now foundation and it's higher. I want to look at work done. Sorry, your accent. Work done. We'll look at work done. And in physics, whenever we are transferring energy from one place to another place, we're doing work. Okay, so I'm doing work now, not because I'm actually doing physics work, but because I'm transferring the chemical energy from the food I had earlier on into kinetic energy when my hand is moving. So I am actually doing physicsy work. I'm doing work in physics terms. To work out how much work has been done, we need to do force multiplied by distance. So work done, cover it with that, equals force, covered in pen, multiplied by distance. And when 1 joule of work is done, okay, 1 joule of work is done when 1 joule of energy is transferred. Converts straight across. So if 1 joule of energy is transferred, a joule of work has been done. 10 joules of energy being transferred, 10 joules of work. Okay, they're directly related. And what the exam may do is they may talk about energy being transferred, but not call it work done. So you'll have to make that connection, guys, between both of those. So please make sure that you're able to recognize that difference. All right. I'm just checking the comments really quick. Can you focus the camera again, please, Millie? I hope that's in focus now for you. If not, send me another tweet. Alfie, can keep all them sheets you're writing on for in the morning. Make sure you sign my book. Alfie, I've still got your exercise book that I've got for you for your leaving present, and I will keep all the sheets. What I will do is actually I'll stick them on the canteen window, okay? Because I might as well stick them up there instead of sticking them online. It takes quite a while to do. Okay, so moving on a little bit because I'm sort of blabbing on. Here we go. So work done, force and distance. Calculate. Let's just say we've got a box. Of course, I can draw boxes. Oh, multicoloured pens, it's smudged. Oh, 3D diagram was good till then. So calculate the distance that box has been moved. If it is pushed with a force of 42 newtons and 50 joules of work has been done. So calculate the distance the box has moved if it's pushed with a force of 42 newtons and the person pushing it did 50 joules of work. We go back to the triangle. Okay. Distance is equal to work done divided by force. My work done is 50 joules. I nearly got the units on then. And then the force is 42. So I will knock out my calculator at this point. Don't forget, you are given a calculator. It's not a mental maths test. Use it. Once again, there we go. So I'm going to do blank fraction button. And those you have taught, we've talked about the blank fraction button. 50 divided by 42 gives me an answer of that. SD. Okay, to make it into a decimal. And we get an answer of that. And I'm going to round it to, let's do it to 2 decimal place. 1.1. I'm going to keep it as 1.1. I know it's 1 point. In fact, to be fair, actually, I've just done the recurring thing there. So it will be, we'll keep it as 1.1. Okay, so I didn't see the recurring there, so keep it as 1.1. And we're working out a distance, so it's going to be in meters. Okay, so if that box was pushed with that force and that much work is done, that's how far it has gone in meters. Okay, so it's a little bit choppy changey, this topic, so we do sort of keep jumping between stuff at the moment. We're now looking at work, we're now looking in our case at work done. Okay, an object. We keep lagging. Sorry guys, let's wait a second. It's a bit laggy. Okay, I think we're back on. Sorry, I'm looking at the actual live video and I notice it does keep lagging. I'm sorry about that. It's the school's Wi-Fi that's a little bit stickly. Such as elastic band, a spring. That means when you apply a force to it, that's supposed to be a spring. That is shocking. It looks like loads of U's. Try again. There we go. And you apply a force to it, so you might stretch it. You might stretch it that way. It will stretch, but when you remove the forces, it will turn back to its original shape and size. That's what we call elastic behavior or elastic deformation. So if something deforms elastically, when the force is removed, it will return back to its original size and shape. The other option is inelastic deformation. So this is when an object, okay, doesn't behave elastically. So if you stretched it and it changed shape and you remove the forces, it will not return back to its original size and shape. The example I always use is blue tack, okay, and I've got some here. So if I stretch it, brilliant, when I let go, it doesn't go back to its original size and shape, it stays in the shape that we've just left it in, so it is inelastic. So make sure you know the difference between those two types of behavior or deformation. Now you could be asked to calculate the forces involved with elastic objects. This involves a triangle, once again. To work out the force applied to an elastic object, we need to know something called the spring constant and the extension. The spring constant, okay, is a number that tells you how stiff your spring is, which is that K number there. Okay. The bigger the number, the stiffer the spring. So a spring such as one in your pen would have a small spring constant because it's very stretchy. It's easy to pull apart. The spring on a shock absorber in a car would have quite a large spring constant because you can't just pull it off and start pulling it apart with your hands. If you ever work with them, you know they're quite difficult to work with. Now, I'm just conscious of the time, year 11, so I'm not going to do a practice calculation on there. Just make sure you know that you know how to use a formula. And a big point here actually is that your distances or extensions must always be in meters. And if it's in, you need to do some conversion. So for the extension, it should be in meters. If it is not, change it and fiddle about with it till it is. You could be asked, instead of calculating the force applied, you could be asked to work out the amount of elastic potential energy that an object has got stored in it. So if you stretch an elastic band, it will have a stored elastic potential energy. All right. Now, just a quick note on this one. If you do 50 joules of work to stretch an elastic band, provided it is behaving elastically, so it hasn't snapped, it hasn't strained or anything like that, provided it is elastic, 50 joules of energy there will be converted, 50 joules of work will be converted into 50 joules of elastic potential energy. Okay, they're directly related. So if you stretch something elastically with a certain amount of work, that will be converted all into elastic potential energy. All right, now to work that out, we need to do half or 0.5 multiplied by the spring constant multiplied by the extension squared. Now, there is a bit of a tricky here because we've been given an extension squared. We've got a square to deal with. So if you ever have to rearrange the equation to work out the extension, okay, I've done a big E, sorry. Cover that up is elastic potential energy divided by, I'm going to do 0.5 there, times by spring constant. The problem is, whatever you work out there is the extension squared. Now, there's two ways to do this, all right, and I'll show you both. The first way is to do it this way. Work all of that out, then at the end, on the calculator, press the square root button, press the answer button, press the equal button. So you rearrange your triangle, do EPE divided by 0.5 times K, then do square root of your answer, so whatever that is, equals, and that will give you the extension. Your other option is to do it all in one go. So what you'd do to work out extension, it would be the square root of EPE divided by 0.5 times K. And you can do that on your calculator. You've got in here, and this is where I keep talking about blank fraction button here, it's this one. That one there, just above my finger. That allows you to put things in as they appear and as we rearrange them. So if you press the square root, which is that one there, fat fingers in the way, and then press that one, and then press that. Okay, you can see what is in my calculator. Sorry, mirror image again. Absolutely shocking at this. There we go. What is in my calculator? There it goes. What is in my calculator looks similar to that one. So you can do it as a one-step calculation, or do square root, answer, and then press equals. Now, obviously, it's just done some random equation, random calculation. What we're left in it, give me a number. Yours will be a real one. Okay. Oops, not the camera. Classic. I think I'm going to be delirious, Mr. Catchall here. I think it's the excitement for tomorrow's exam. So, to work out the distance an object has travelled, velocity multiplied by time. You'll have done it at key stage 3 is distance, speed, and time. I've included that as well. Distance, speed, and time. Distance, velocity, time, same thing. Okay, just make sure you link that together. Now, as well as doing that, now there's no squares here, so cover up what you're looking for. So velocity is speed divided by time. Time is speed, is distance divided by velocity. Okay, so velocity is distance divided by time. Time is distance divided by velocity. Distance is velocity times time. So you can just treat like that you would any normal thing. One thing the exam board has put in their specification very clear on is the fact that you are able to recall typical speeds. Now, I have drawn there some wiggles. Those wiggles stand for approximate. Because if you've got someone, for example, who's 6.5 foot tall, they've got really long angular legs, they may walk quicker than someone who's 5 foot tall with little short legs tottering along really quick. So it's an average, okay, or an approximate speed. The approximate speed for someone running, for walking, is approximately 1.5 meters per second. The approximate speed for someone running is 3 meters a second. The approximate speed for someone cycling is 6 meters a second. The approximate speed of a moving car is 30 meters a second, and a reference number here don't be approximate. The speed of sound in air is 330 meters per second. So please make sure that you're able to recall them. So a question may say to you, calculate how long it takes someone to walk 5 meters. So calculate how long, so calculate the time equals distance divided by velocity. Calculate the time it takes someone to walk 5 meters. 5 meters, but you're not given a velocity. Oh dear. Well, you have been given it. It'd be 1.5 meters per second. All right. Quick question, Joe. When does foundation finish? This is foundation. Unless I say high tier only, it's all foundation. Now, I have gone on because this is probably the largest topic out of all of them across all sciences. When you were taught it in year 10 at Horizon, it took from Christmas till June. So we're probably looking at around about 7:30, maybe even a little bit later. We are going to have to play it a bit, but I will speed up a little bit on this one, guys. I am sorry, but as you can appreciate, it's a bit of a big topic, because there are waves coming and also electromagnets, but waves is fairly decently sized. Electromagnets is fairly shortish compared to these two. It's relatively tiny. Okay, so remember your speeds, put them in equation. Higher tier only bit, higher tier alert, whap, 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 higher tier only, motion in a circle. Why or how can an object have a constant speed but a change in velocity? So we've got a roundabout. All right, let's say this is roundabout when you get off M1 to come to Stoddard Road, and I'm going roundabout at a constant speed of, let's say, 20 meters a second. I'm not going full pelt because I'm going round and I'm being a bit cautious. I've got a constant speed, but my velocity is changing because my direction is changing. Compass terms, I'm going north, northwest, north. We're going down to, not saying north, yeah, we're going north, well, you get the picture. We're going up, then we're going down a little. I'm getting myself confused with my compass. But because my direction is changing, my velocity is changing, but my speed is constant. So just a little aside there, where you could be asked to work out or explain. For example, the one that's on the exam database is the Millennium Eye in London. Why, for example, it moves around constantly at 1 meter per second. Why is its velocity changing? Well, because a pod is changing direction. Back to foundation and higher tier, so back to normal stuff here with this one. We've got a distance time graph. You need to know what the lines represent and what you need to do with them. If you've got a line going up, something is moving away from the starting point at a constant speed. If a line's straight, it's a constant speed on the distance time graph. If the line is flat, an object is stationary, not moving. If it goes down again, it means returning back to the starting point. So imagine you set off to school, you wait at the bus stop, you think, oh my days, I forgot my EPE kit, you turn back round and you go back home. All right, and then you carry on and go straight to school. So once again, we're moving away. If, and this is a higher tier only, so this is where it does very intermingle, this little section now I'm going to say to you is higher tier only, and I'll do this over here, and I'll put a little HT. If the object is speeding up on a distance time graph, you may get a curve. Okay, that bit's higher tier if you need to know what to do with that. The rest is foundation and higher. All right, so I know it's a bit confusing, but that bit with the curve is higher tier only. You could be asked to calculate the speed of an object from one of these graphs. To do that, we need to use the gradient. So for the gradient, we need, put it here, change in y divided by change in x. To do that, you will have done it using a triangle. So we work out how much it's gone up by on the y-axis. So it might have gone up to 10 meters there. Work out how much it's gone up by on the x-axis. So let's say the person's traveled 10 meters in 5 seconds. 10 divided by 5. So the speed will be 2 meters per second. So it might be power walking, for example, there. I think that's our compared values. The higher tier bit is being able to draw a tangent. Okay, now you will have talked about it in chemistry, rates of reaction, all that stuff. The tangent, it may say, calculate the speed at that point of the speed at that point there. So a tangent is a line that touches a straight line that touches the curve at that point there. Now, obviously, I've done it with fat pen, so it doesn't quite touch. Sorry, put that. Triangle is not triangle, like we've just said, would then come from that triangle, from the straight line there. So foundation, doing all that and higher. This is higher tier only, knocking out a tangent to do that bit from there. Okay. Acceleration. Acceleration is the rate. The rate of change of velocity. If an object has got a positive acceleration, it's speeding up. If it's got a negative acceleration, we say it is decelerating, and it's actually slowing down. So if at any point on an exam question you get a negative acceleration, it isn't wrong. You've not done your question wrong. You're not going to fail. Your life isn't over. You don't need to sit and cry. It just means the object is not speeding up. It's actually slowing down. It's getting slower. And the formula you may be asked to calculate acceleration with is a couple, but the easier one that we're going to look at is final velocity, take away initial velocity, divided by time taken. So the final speed it ends up at, take away the starting speed, divided by the time. And that's why you might get, if you've got an object slowing down, for example, you might have a car that started at 30 meters a second and then went to 0. So the final speed is 0, the starting speed was 30. And let's say to come to a stop, it took 10 seconds. 0 minus 30 is minus 30, divided by 10. Okay, so 1 second. Minus 30 divided by 10. Oh, broke it. And then it gives you an acceleration of minus 3 meters per second squared. So that isn't wrong. It just means the object's slowing down. And you can see that's where the negative number comes from. Okay. Why am I telling you this? Well, because you could be asked to, you might be given a velocity time graph. Now, please, 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 please check here. Check the y-axis, because if it's distance time graph, it will say distance. If it's a velocity time graph, it will say velocity. And depending on what graph it is, depends on what the lines mean. So, for example, if we've got an object, a graph for a velocity time graph, and the line is going upwards, we have got something that is accelerating. Oh, an orange pen, I messed that one up. That's better. Accelerating at a constant rate. If it's not, it'll be a curved line again. If the line is flat, you've got something, it's not stood still, it's a constant speed now. So you'll notice now some similarities and differences. So if you've got a flat part of your graph, it's a constant speed or constant velocity. If the line went down, I mean, it hasn't here because I wanted an example for something else, but if the line went down, the object isn't going back to the starting point, it's actually slowing down, its velocity is decreasing. So it could be, for example, you're pulling onto the slip road for the M1, you get up to 70 miles an hour or 30 meters a second, you state your constant speed, you want to overtake, so you drop it into third, you bomb it, put your foot down, and your velocity increases. But then, for example, you may get to the end and pull off, your line will go back down to 0 like that. Okay. Now the gradient of this part, the gradient on the velocity time graph isn't, in our case, like we've just done, working out in our case the speed. It's actually being able to work out the acceleration. So the gradient on here equals the acceleration, and you follow the same procedure. Triangle, same as before, y divided by x, tangent if you need it. Higher tier only bit, higher tier only alarm again, is this bit here. If you are asked to calculate the distance an object has travelled from this graph, to do that we need to use the area under the line. Okay, so triangle again, and then the area of a triangle. So let's say in 5 seconds, for the first 5 seconds, the velocity of the object was, it went up to 30 meters a second. So to work out my gradient, work out my distance, I need to do the area of a triangle, which is base times height over 2. The base is gone from 0 to 5. The height is 0 to 30. Now we're going to half it. Okay, 5 times 3 is 15. Stick your knot back on 150. Divided by 2. Okay, and you probably hear me tapping with my calculator. I just wanted to check. It comes out at 75 meters. Okay, so in that first 5 seconds of the journey, the car has travelled 75 meters. Once again, velocity time graph, calculating the gradient is a foundation skill. Being able to work out the distance the object has travelled is a higher tier only skill. So that's all higher tier. If you asked to work out the distance from this bit here, you'd work out the area of that bit first, and then the area of that bit, because that is all the area under that part of the graph. Okay, so you would need to talk about both sections. So you'd work out the area of that bit first, so base times height over 2. This bit here would be base times height, and then add them together. All right. If you've got any questions, like I said, our Twitter is at HCC_depth of psi. Send us a tweet, use a hashtag, ask all one thing. Sorry, I put space in. I want to do my joint handwriting. Ask Team Sci. So hashtag ask Team Sci, and we are HCC_depth of psi on that one. Now, the one that a lot of people dread, a lot of people panic about, and if you did the second specimen paper for your mock exam, Horizon students on higher, and on foundation actually it came up, you did a question where you were required to use this formula, okay? It's what we call a formula, what we call uniform acceleration. Uniform means same. That's what it means, uniform. So you wear a uniform at school, means same. You all wear the same stuff. So first of all, now I know I'm going to pick this part a bit with you a little bit. So v squared is your final velocity. And it is squared on this one. You do need to square it. U squared is initial velocity. The 2 is just there. Just in a moment when you do it, we'll do 2 times A times S. Okay. A is acceleration. S is distance. Now we've got a bit of a problem here, kids, because we can't put this into a triangle because there's 2 subjects either side. So it's very difficult to start putting this into a triangle. And this is where you have to deploy a math skill. And the way you treat this is the way you would treat anything in maths, where your maths teacher would say the words to you, make X the subject, or rearrange the equation to make something the subject of the formula. You treat it just as you would for that. So I'm not going to go into the rearranging math skill with you, okay, because I'm conscious of time and it is something you should be okay with. If not, we'll look later when we get to the questions and answers. If you're working out your final velocity, it would be u squared plus, and bracket this as well, 2 times acceleration times distance. Okay. If you're being asked to work out acceleration really quick, asked to work out your acceleration, it's going to be velocity squared, final minus initial squared, divided by 2. I'm just getting a time check from Mr. Catterall. 2 multiplied by distance. To work out distance, velocity, again, same as before, 2 times A. Okay, so please make sure the biggest thing for this question is knowing how to rearrange the formula, and also knowing knowing this value here, the acceleration due to gravity. You must be able to know that number and assume it. If a question doesn't tell you the acceleration, so it might be an object falling out of the sky and speeding up, okay, and you might be asked to calculate what is the final speed of an object of a skydiver falling out of a plane in the first 500 meters of the first 500 meters of their jump, or it could be how far does a skydiver travel when they jump out of a plane and they reach a speed of 100 meters per second, for example. Okay, so you'd be given the final. You'd be asked to you'd be given the final speed. Your initial speed would be 0 because the sun's still in the plane. You wouldn't be given the acceleration, and you've been given a distance. So you would have to assume that acceleration will be 9.8 meters per second squared. Okay, so please remember that value because it is one that you may have to recall at a certain point. Okay, so I want to look at the law, Newton's laws. Now I've touched on the first law. Okay, that was the one where I'll just flash a sheet really quick, but I have spoke about this already. It's the one. No. That one, not that one, not that one. I'll have it to hand. Where's it gone? Come here. Get here. Here we go. This is Newton's first law. It's that one. So earlier on, I talked about that in the video. Please rewind when it comes up and uploads afterwards to watch that one on there. So Newton's second law of motion is all to do with force, mass, and acceleration. Okay. So to work out the force applied to an object, you need to know the mass, you need to know the acceleration. To work out the mass of an object, you need to know the force and the acceleration. To know the acceleration, you need to know force and the mass. Now, part of Newton's first law is all to do with things that are proportional. Okay. Now, the biggest one here is that force is proportional, directly proportional. Thank you, sir. It looks a bit like a funny fish shape like that. Directly proportional to the acceleration. So if one goes up, the other goes up by the same rate. Force, acceleration, and mass are inversely proportional. Okay, so that means if one goes up, the other goes down. And when you did your required practical, pushing your car down the ramp, that is why you did it, to prove this is true. To prove when that goes up, that goes up. When that goes up, that goes down. And when that goes down, that goes on. There's a little bit of common sense in there, a little bit. Okay, if you increase the mass of something, it's going to speed up slower. That's the way to think about it. If something's heavy, it's going to accelerate at a slower rate. Whereas for force, if you're pushing, I don't know, if you're pulling someone on a sledge when it snows, and you pull them a little bit of force, they're going to speed up quite slow. If you proper yank them at full speed, they're going to speed up really quick. So just apply some common sense to that, year 11. It's not that difficult when you think about it from a simplified point of view. Okay, third law. Every action has an equal and opposite. Look at speed writing in different coloured pens. Equal and opposite reaction. Examples that are used in exams are people ice skating. So you've got two people ice skating. You've got someone there. And you've got someone here. Okay, and they push against each other. So person A pushes against person B. What happens? If they're pushing against this person, we're just going to use one example actually. If they push A pushed against B, B is going to move that way, but A will move backwards with an equal and opposite amount of force. So if they push, person A pushes person B with 10 newtons of force, person A will move backwards with an equal and opposite amount of force of 10 newtons. Okay, that's all Newton's third law is. It's all about equal and opposite, guys. What they will do is they will apply it to various situations. So people ice skating. When I taught it, I sat on a computer spinny chair, put someone else on a computer spinny chair, and I pushed them. They went forwards, I went back. However, if they start to dig deeper with this question, guys, it's important that if the mass isn't the same, then the force won't always necessarily be directly the same. There will be some variations with the forces both ways. Okay, we've only got a couple of bits left. I'll have a quick break and you'll be with Mr. Catterall, who'll talk you through waves and electromagnets, and then we'll take the separate one students through the separate zones bits as well. Please note we are not doing space physics tonight. We have uploaded a pre-recorded video of that because we predicted this was going to take forever in a day. So we've got a pre-recorded video of space physics. Right. Stopping distance. To calculate the total distance in meters that it takes, I'm going to use a car throughout as an example. A car to stop, there are two components involved. Okay. The first bit is the thinking distance. This is the distance that your car travels whilst you are reacting to the situation, or the distance your car travels while you think, right, I need to brake. Your brain processes that thought. It then sends an electrical impulse all the way down through your nervous system, down to your foot, to your effector and makes your foot go onto the brake. That's your thinking distance. There's also a braking distance. This is how far your car travels from the moment you put your foot on the brake pedal to the car going to a complete stop. Okay, and to work out a total stopping distance, all you would do is add them together. That's all it is. So let's say your thinking distance is 10 meters, your braking distance is 40 meters, the total stopping distance will be 50 meters. That's all it is. Okay, so just be aware. They may ask you to work out that. They might give you them two and say, what's the thinking distance? Oops, knocking camera, getting excited. Just come down a bit. They might give you that and say, what is the braking distance? They may give you them two and say, what is the stopping distance? So just be prepared to swap and change. Pen is on one about. There we go. You could be asked about factors that affect thinking distance and braking distance. So actually, what things could make that distance longer? What things could make that distance longer? And there's a few you need to know. The way I teach is I always say there's a few dead certs that if you put, you will guarantee to. Some people say, well, what about if a pigeon is in road? Or what about if I see my nan walking side of the street? Or what about if I run out of petrol? Or what about if it's something else? Don't go airy-fairy on this. Keep it simple, keep it straightforward, and keep it to dead cert answers, okay? So things that affect your thinking distance, factors that can affect it. Drugs. Okay? Alcohol is a drug. It has a physiological effect on your body, bit of biology there, so it can affect your thinking distance. Now, usually, they will ask you what things can increase your thinking distance in there. So drugs, alcohol, okay? Some drugs, yes, do make you more alert. So people say, yes, sir, what about ecstasy? Yes, it does increase you. It can increase your reaction, make you more alert. However, some people react differently to drugs in different ways. You know, examples like that. It can increase that distance. Okay, so drugs, distractions. Your phone. Trying to connect Bluetooth on your phone. Pick it, or your phone's ringing because your mum or dad's phoning you. Can distract you because you're looking at your phone. So actually, it takes you longer to react to a situation, so your car travels a longer distance. Okay? People. If you've got mates in your car with you, they can distract you. Small people, children. Okay, if you've got little people in the car with your children, a big distraction. Your parents or your friends, or if you know people with kids or you ain't car kids, you know they make a right racket sometimes and they can put you off and distract you. All right, so those are particularly the biggest ones that can affect your thinking distance. Okay, factors that can affect your braking distance. These by no means least a comprehensive list, guys. These are just dead certs that you can defo get. Road conditions. If it is raining, okay, if it is raining, then it might increase your braking distance. If you are traveling on ice, that can also increase your braking distance because it means you're going to travel further. It takes up to 10 times longer for a car to stop on ice compared to normal road conditions. Condition of your brakes. If your brakes are dodge, it's going to take you longer to stop. There's also there's a little bit of a renegade answer in here, a little bit of a maverick that goes across all or both of them, and that is speed. The faster you are traveling, the further your car will travel whilst you're reacting to something. So your thinking distance will be longer because you're traveling faster, so you're going to cover more distance. And braking distance, because the faster you go, the longer it takes you to come to a stop. So actually, that will include both. Okay, so dangers. This is really quick, a little bit of an aside. Dangers of large decelerations. So basically, why doesn't everyone travel around bombing it at full speed and then slamming brakes and doing emergency stop all the time? Okay, the biggest problem with that is with your brakes. Okay, that's a brake. You've got a brake disc there, and then the bit on top that clamps on. If you are doing a large deceleration, okay, you've got to remember the force involved with braking. We've got kinetic energy here. Okay, energy is transferred from the movement, in our case, to the brakes by friction. Energy is transferred, work is done because of friction. So the movement energy goes to heat energy, or if we're being fancy, thermal, which we should use a fancy word. If there's lots of thermal energy, these brakes here can overheat. If they overheat, they are less effective. Okay, so that means they will not be as effective as normal brakes, so it will take you longer to come to a stop. So that is one of the biggest dangers of large decelerations. Okay, the last bit now is looking at momentum. All right, now momentum, let me just double check, is a higher tier only thing. I'm just going to bear with me. I think it all is. I should know. Yep. All of momentum, higher tier only alert. This is all higher tier only. Okay. Momentum is basically what something has when it is moving. If something's moving, it has momentum. Okay. Why? Because momentum is linked to mass and velocity. So if anything is moving, it has momentum. So you could be asked to calculate momentum using mass and velocity. Okay, now momentum is measured in something called kilograms meters per second. Mass is in kilograms, velocity in meters per second. And look, right? If you can't remember units for momentum, put them together. That's all it is. Okay, so just chuck them together for that. Now, conscious of time, so I'm not going to do a practice question with you on that, guys. It's the same as any other formula with 3 subjects. You just rearrange it as you would normally. Just be aware your mass may be in grams, naughty, kilograms. Yes, you must do a conversion on that one. The last little bit is looking at conservation of momentum. So, for example, it could be the question I did today with my year 11s was somebody on a boat who jumps off the boat into the sea. What you must remember is the total momentum before an event or a collision, whatever, is exactly the same as the total momentum after. So if the momentum before something happens is 0, the momentum after is 0. Now, talking about my example about someone on a boat, this is where people get confused. Right, let's have the deep blue sea. That's quite good. And let's have a boat. It's not going to be a fancy speedboat. Sorry, everyone. It's literally going to be a dodgy like that. And we've got a person. We've got a person on there, and they're jumping into the sea. Okay. Before the person jumps, the total momentum is going to be, keep picking pens up and chopping, total momentum before is 0 kilograms meters a second in total. After, that must mean the total momentum is going to be 0. However, that gentleman or lady is jumping in. So if we think about calculating their momentum, let's say their mass is 50 kilograms. And the velocity, so they're diving in at a velocity of 1.5 meters a second, okay? Their momentum is going to be 75 kilograms meters per second, and that's just for this person here, all right? So that must mean if that person's got positive momentum, because they're going for the jumping out into thing, the total momentum needs to be 0. So that must mean that the boat has momentum of minus 75 kilograms meters per second, okay? Because the total momentum before is equal to the total momentum after. So if the person there has got 75 kilograms meters a second, to make the total momentum afterwards 0, the boat must have an equal and opposite amount of momentum, which is minus 75, okay? They could apply that to various things. It's sometimes with collisions. So on your mock, if you do specimen mock paper at Easter, the second one, it talked about gliders on an air track. You'll notice I've not really talked about air track on here. For the required practical and acceleration, the exam board have said on the new release that you don't need to use an air track. So it's just pushing a car down a ramp. If you did it in year 10 last year, you may have used an air track. Literally, it's basically a track with air that pumps out, reduces the friction, and you shove things and they go up and down it, okay, push them up and along. That concludes year 11, our trilogy, higher and foundation set of revision, okay? But that's only for forces. We are going to switch now. We'll have a 2-minute break, literally genuinely 2 minutes, and Mr. Catterall is going to talk you through the foundation and higher waves, which is fairly long, if not too long, and electromagnets, which is tiny. Okay, just to answer a quick question, Joe, is waves foundation as well? Yes, it is, my dear. I'm getting ready for my dinner in 15 minutes. I hope your tea is nice. Let us know what you're having. This will be uploaded afterwards, so please watch this little bit when you get finished. Okay, so really quick 2-minute break. Oh, I've drawn on sheets on the table. Quick 2-minute break, and then Mr. Catterall will be back, and we'll be taking you through your waves and electromagnets.
Okay, ladies and gentlemen, welcome back. We're going to go through waves now. Now, let me just make it clear for you, for trilogy, okay, waves isn't a big topic. So if we actually look here on the purple sections, all right, therefore trilogy, higher and foundation, the red parts are the extra things for physics only. So we're only going to do the trilogy ones, and then we'll come back later and then do the extra things for physics only. So first thing that's really important for this section is the wave equation, and the wave equation is V equals F multiplied by lambda. Okay, so let's remember that V is our wave speed, and it equals frequency multiplied by the wave length. Okay, so think about this for the units: speed, meters per second, frequency is hertz, and wave length, okay, is meters. All right, now this is the equation that you're going to have to use within this topic. If we use the magic triangle, okay, we have the V at the top, F multiplied by lambda wavelength there. Now, it's really important that we actually remember what the definitions are of these things. So wave speed is how fast the waves are traveling. Frequency is how many waves pass a single point in 1 second. So frequencies pass a point in 1 second. And wavelength is the length of one complete wave. Now, with that in mind, okay, I'm just going to use a diagram here that I've pre-prepared, and we're going to identify some of those key things that we need to know about this, this wave. So firstly, if I want to know the wavelength, there are a number of ways that I can actually calculate it from this diagram. Now, the first one is by actually here at the start, going one complete crest, one complete trough, and that distance between point A and point B, okay, that is one wavelength, okay? So that's the first way that I can work out a wavelength. The second way that I can work out a wavelength is I can actually go from the middle of one crest to the middle of the next crest, and that would be a wavelength, one wavelength. Or I could go from the bottom of the middle of a trough to the middle of a trough, and that would be a wavelength. Okay. Now, let's just remember what some of the names of these things are. So this is either a peak or a crest, and this is a trough. We can see how to work out the wavelength. And then the other thing that we need to remember to be able to add to this is what's the amplitude. And the amplitude is the distance from the center line to the top of a peak or crest, or the center line to the bottom of a trough. Okay, so those are where our amplitudes are. Now, what's really important is that we need to actually be able to explain what those words actually mean. So if I look at this diagram and we look at this center line here, I'm actually going to put a 0 on it, or I'm going to use the word rest. Because when I'm talking about the definition of amplitude, I'm actually looking, so amplitude is the maximum displacement from 0 or rest to the top of a peak or bottom of a crest. A trough. It's been a long day. Okay, so it's the maximum displacement. So in other words, it's the furthest movement that that particle actually makes within that wave. Okay, wavelength, we've actually said, is the distance between a crest to a crest, a trough to a trough, or one complete crest and one complete trough. And then the next one is frequency. Now, we actually said that frequency is how many waves pass a point in 1 second. Now, the whole of this picture represents 1 second. Okay, so what we need to really think about is being able to work out how many waves are actually, complete waves are on that picture. And this is something I could ask you to do in the exam. So I'm going to go from A to B. That is, let me get a different color pen so it stands out. So from A to B, that's one wave. From B to C, that's 2 waves. And from C to D, that's 3 waves. So this wave pattern has a frequency of 3 hertz. There are 3 complete waves passing there at 1 second. So if, for example, I'd actually been told that the wavelength was 2 meters, I can then use my equation, and V equals F lambda, to work out the wave speed. So if V equals F lambda, my frequency is 3 multiplied by 2. So 3 times 2 equals 6 meters per second. So that wave actually travels 6 meters per second. Now, one of the other things that they often actually ask you, they will show you a wave pattern, and here I've got a wave pattern, and they'll ask you a question like, for example, is wave pattern 1 the same as wave pattern 2? Now, often students will look at that and say, well, no, because they're different. Remember, any of these diagrams are a snapshot in 1 second, okay? So this is representing 1 second snapshot. So in diagram 1, that's 1 second snapshot. Diagram 2 is 1 second snapshot. So let's think about using the diagram to work out some of those key things that we've just looked at. Let's work out the wavelength, and let's work out the amplitude, and let's work out the frequency. So the first thing that I'm going to do is I'm going to look at the amplitude of wave 1. And I can see that the amplitude of wave 1 is 0.5 minus 0.5. Okay? I'm going to look at the amplitude of wave 2. So if I go from here down, I can see it's 0.5, minus 0.5, and from here up, I can see that it's 0.5. So at the moment, I'm going to put A for amplitude equals 0.5. All right, they're both the same. I'm now going to look at a wavelength, okay? And I can see here that one wavelength, one trough, one from crest, it ends at 4. If I look here, from my peak to my next peak, peak to peak, the peak to peak ends at 4. So I can see for both of them that my wavelength is 4. And then let me do my frequency, which is the last thing. 1, 2 waves. So 1 there, 2 waves. And then here, 1, 2. So my frequency is 2. So because I've looked at that carefully and I've compared them, I can actually say that those two wave patterns are exactly the same. They're just showing different time intervals. So it's the same wave. Okay. So just remember that. It's one of the things of how you actually have to apply your understanding of amplitude, frequency, wavelength, and wave speed. Now, we're going to go on and have a look at what transverse and longitudinal waves are. So I've got a little diagram here to help us with it. Now, this is a diagram of the slinky spring experiment. You've probably done this with each of your teachers. I know with my class, I use my big rainbow slinky. Now, in order to make my slinky make this pattern, I have to shake it side to side, okay? And if I was actually drawing it on a graph, all right, I'm just going to put an axis here. It shows that it goes like that, okay? All right, my slinky is going side to side, right? Now, a transverse wave, all right, this is when the vibrations of the particles are perpendicular to the direction of energy transfer, all right? So we can actually see here, and I've written it here, the vibrations, okay, are moving up and down. Now, if you take this bit of the spring here, I'm just going to colour it in, all right? It cannot move that way or that way. It can only go up and down. So that, if it is a particle, it's moving up and down. However, the energy transfer of the slinky spring is going in this direction. So when we say it's perpendicular, all right, I'm going to write that down, perpendicular, all right, so the vibrations are perpendicular or at right angles to the direction of energy transfer. And that's a key definition that you need to remember. Now, a transverse wave can also be what we call a mechanical, whoops, spell it right, a mechanical wave, all right? And one of the things that they could ask you is, give an example of a transverse wave. So good examples of transverse waves are water waves. You could say radio waves, microwaves, visible light, infrared, ultraviolet, X-rays, gamma rays, okay? Basically, any part of the electromagnetic spectrum and water waves are transverse waves, and they act in this way, that the particles vibrate up and down at right angles to the direction of energy transfer. We've then got longitudinal waves. Now, longitudinal waves, and again, I've got a picture here of a slinky, all right? And with this slinky, we pushed it backwards and forwards, backwards and forwards. And what we actually caused the slinky to do, we got parts of the slinky to actually squeeze together, all right? And they were under compression, it's shown here. And the other parts of the slinky were actually spread out. They were far apart. They're what we call a refraction, okay? And the slinky was vibrating left to right, left to right, left to right. Now, the energy is transferring in the same way as in the last diagram with transverse waves. However, the vibrations are in this of the particles are in the same direction, or we say they are parallel. So the vibrations of the particles are parallel to the direction of energy transfer. Okay, so they're going backwards and forwards, backwards and forwards, backwards and forwards. So those particles are just moving backwards and forwards. Now, here we've got a picture of the actual particles. So that's on a sling. This is on like the particles in air. And what you can see is we have sort of like areas here and here, okay, and here, and here, and here that I'm colouring in, that the particles are closer together, all right? So these would be our areas of compression. And then where we've got particles where there are fewer ones, here would be a refraction. Now, one of the things I could ask you, like it's shown here on the diagram, is from this diagram indicate one wavelength. Now, the easiest way to represent a wavelength is to go from the middle of one compression to the middle of the next compression. So on this diagram, it would be from that point to that point, and we'd be able to measure it. On this diagram, I could go from here to here, and that would be one wavelength, okay? I could go from here to here, that would be one wavelength. Now, it's always better to do the middle of a compression to the middle of a compression. If there aren't two compressions, but you've got a compression and then some refractions, okay, do the same thing, middle of one refraction to the middle of the next one wavelength, okay? Now, you only need to remember, okay, one example of a longitudinal wave, and that is sound, all right? So just remember that transverse waves are any part of the electromagnetic spectrum and water waves, whereas longitudinal waves are only sound waves, okay? Now, I'm going to go on and just look at how waves actually behave, all right? We're going to look at refraction. So you would have done an experiment where you have taken a glass block or a perspex block, so I've drawn it here, okay, and you shine light into it. Now, if I shine light, okay, into my perspex block or glass block, I'm going to put here block, I'm going to put here air and air. If I shine it in at 90 degrees, I'm just going to use a ruler, because when we actually do these diagrams in your exam, anything to do with light, you must use a ruler. So if I shine the light hitting the block at 90 degrees, and we can see here that's 90 degrees, what will happen is it will pass straight through, okay? The direction will not change, okay? Now, that's really important, because that line going straight through is what we call our normal. So when light normally hits a surface at 90 degrees, it travels straight through it when we're looking at refraction. However, if I actually take my glass block again, all right, and I'll draw it very quickly. And this time, the light hits the glass block at an angle, so I'm going to draw it on. So you could have a diagram like this, and it says, complete the diagram to show how the light behaves as it goes into the glass block. Now, it's worth a few marks, this, so you must use your ruler. So you've got your line, okay, which is your incident ray. The first thing is take your ruler and draw a dotted normal line, okay, like I've done, and label that as your normal. That's going to get you a mark. Now, there's a rule that we've learned, that when light enters a denser material, okay, it slows down. So our block is denser than air. So this means light slows. And it slows, and that means that it's going to bend towards the normal. So I've drawn my light there, okay, and I'm going to put a little arrow on it. And okay, now the way that I know that, if I look here and I draw an angle here, and I'm drawing my angle from a ray of light to my lines are touching. When we draw these diagrams, it's very important that every single line touches. If there's a break, that says our light has stopped. Now, it's traveling out of the block, so I'm going to put another normal in like this, because it's going to get me marks. Okay, and this time, because it's going from a more dense material to a less dense material, all right, it is going to bend away. Now I'm going to do a little neat trick here. I'm just going to put my ruler on. I'm going to drag it across, line it up, and using a fat pen, so it's a bit more difficult. I'm going to put that on there, put my arrow on it. If I then do my angles again, smaller angle, okay, bigger angle, and they look roughly the same. So there you are. What I've drawn there is a really neat diagram to show the refraction of light through a glass block. So let's just remember the key facts. When you're going from a less dense to a more dense material, light slows and bends towards the normal. Okay, so that's this section here. And then when it goes from a dense to a less dense material, it bends away from the normal. So just remember that. It's a common thing that they like to actually put onto the exam, okay, for you to, okay, but it's a wavefront diagram, and this is higher tier only, okay? So wavefront diagrams, higher tier only, all right? Now, what I've done here is I've drawn, or I should say I've printed off and stuck on here a picture of a wavefront, okay? And I'm just going to draw it out to show you how easy it actually is. So I've got a line here, and this line represents the boundary. And it's the boundary between a more and a less dense material, okay? Now, I've got an arrow here, and that arrow is just representing the lines that I've drawn here, okay? Now, you can see here that what I've got, and on your exam, they won't have those arrows. So I'm going to draw a wavefront. They might give you a diagram like that and say, complete the diagram to show how the wavefront behaves, okay? Just remember each of these lines, so the line is like the crest of a wave. So I'm just showing how many waves are going there. So if we look at our diagram, all right, our wavefront hits the surface, okay, then, all right, it's going to go bending, okay, and all I've done there is I've shown how the actual wave behaves. And the key thing they're sort of like looking for, and there might only just be like one or two waves here, it's around this bit to show that the wave actually bends. So that one is like that and a bit like that, okay? The diagram's not brilliant. So just remember that your wavefront diagrams, okay, are just another way of drawing your lines. So if I was just drawing a simple line with my ruler, I go like that, and then like that with my arrows on it. My wavefront diagram is just repeating that, but instead of a line, it's a set of waves, okay? It hits here, bends down, hits here, bends down, and then it's off like that, okay? So just remember that. I will go through a wavefront diagram for reflection for separate science students and go through reflection after this. Now, essentially, we've only got a few more things to do on waves for the trilogy students, and that comes down to remembering the electromagnetic spectrum. Okay, so I've actually got in front of me here a wave pattern, and that's representing the electromagnetic spectrum. Okay, and the first thing that you've got to be able to do is you've got to be able to tell me that the electromagnetic spectrum is what we call a continuous wave. Okay, a continuous wave. Now, if you look at this wave, it goes continuously. There are no breaks into it. So every single part of the electromagnetic spectrum blends into each other. Now, I could give you a diagram tomorrow like this of a wave pattern and say this wave pattern represents the electromagnetic spectrum. Can you tell me which end is which? So the first thing I'm going to do is I'm going to look at the picture and the numbers. And I can see here from peak to peak here, there's a big distance, where from peak to peak here, there's a short distance. So I can say that the wavelength here is longer than the wavelength here. So I'm going to say at this end, I've got a long, I'm going to use the shorthand for wavelength, and this end has got a short wavelength. I can look at this and say, well, how many waves are up here? There aren't very many of the waves up here, but here there's a lot more. So this has got a high frequency, and this has got a low frequency. So now that I know that that's the long wavelength, low frequency, that's a short wavelength, high frequency, I can start to think about putting the parts of the electromagnetic spectrum. Okay, and I only have to put them roughly where I think they are. So I'm going to remember a mnemonic that I've learnt, which is Ryan, my improper vicar, uses X-rated gags. Okay, now I've learnt that since I was about 12 years old in science. All right, and it helps me to remember the parts of the electromagnetic spectrum. Okay, now Ryan stands for radio waves, and I know that radio waves have a long wavelength and a low frequency. So I'm going to write here radio. And then the M stands for microwaves. So I know that microwaves come next. And then after microwaves, I have infrared, which is going there. And right slap bang in the middle, I've got visible light. Then next comes ultraviolet. Then I have X-rays. And then I have gamma rays. Okay, so by remembering my mnemonic, Ryan, my improper vicar, uses X-rated gags. Okay, I've learnt the order of the electromagnetic spectrum. And one of the things you could be asked tomorrow, particularly on foundation, is to fill in a missing part of the electromagnetic spectrum. On higher, it could be put the whole thing together. Okay, so there's our electromagnetic spectrum. Now, we also need to know what each part of the electromagnetic spectrum is used for. Okay, so if we think about radio waves, now radio waves have got a long wavelength. Okay, that's one of its properties. All right, and we use them for communication. So radio waves is for communication, and we use it because they're able to travel long distances. Also, they have the habit of, if this is planet Earth here, there's the atmosphere, okay, there's my radio tower, okay, they actually bounce off the atmosphere and travel further. So that's why we use them. Whereas microwaves, we do use them for communication, but we use them for satellite, okay, communication. And that's because, unlike radio waves, there's our atmosphere, okay, there's our transmitter, they actually can travel through the atmosphere, and there's my little satellite, and it's sending it back so you can watch your Sky TV. Okay, they can travel through the atmosphere. All right, so that's why we use them. Then we've got infrared. Now, infrared, we use them for remote controls, but the main thing you need to remember is we use them for heating and cooking. And infrared is thermal radiation. All right, so just remember, infrared is thermal radiation. Now, visible light, the only thing that you need to remember is visible light is used for fiber optics. Now, fiber optics are a way of being able to communicate and transmit information really quickly at the speed of light. In fact, you're actually watching this video because it's actually going from this live stream to a central server somewhere in the USA or Iceland, and it's coming back to you to watch in Barnsley or wherever you are. And it's doing that at the speed of light because it's going down little tiny glass fibers the size of a human hair, and that glass fiber can carry thousands of pieces of information. Okay, so remember, visible light, it's for communication using fiber optics. We then have ultraviolet. Now I'm going to do the next ones in red because all of the next ones are dangerous because they have that short wavelength and that high frequency. It means they've got lots of energy. So ultraviolet, sun tanning. Okay, so if you go out now this time of year, so use lots of sun cream. That's because of the UV, the ultraviolet. Okay, it actually makes your skin go brown. All right, we can also use ultraviolet for security on banknotes. So if anybody actually takes a banknote, like a £10 note or £20 note in a shop, and they stick it under that little blue light, they're checking to see whether it's dodgy or not. Then X-rays is medical imaging. And that's because X-rays will pass through soft tissues and reflect off, okay, are not absorbed by bones. And then gamma rays, again, is medical, all right, and that's for killing cancer cells. Okay, all right, so these are danger. These are dangerous if we're exposed to them too much, okay? So again, we've got to think about, all right, the uses of those materials. Now, essentially, for Trilogy, Higher and Foundation, that is it for waves. Now, I'm just going to show you again, for separate sciences, we've got all these extra red parts that we need to know, okay? So just remember, you need to know your electromagnetic spectrum. It's a continuous wave, the order of it, that it goes from a long wavelength and a low frequency to a short wavelength and a high frequency, or vice versa. Okay, radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, the uses, okay, and which end is dangerous. Now, we're going to go on now and go through the magnets and electromagnetic part for Trilogy, okay, Higher and Foundation. So again, you can actually see from this breakdown that we don't actually have a huge amount of information that we need to go through, okay, and I'll highlight which parts are higher for higher tier students only, okay. So if we start off with the basics of a magnet. Now, if we take a magnet, I'm going to use Miss Nares's favourite colour, brown. So here I've drawn a bar magnet, okay? And that bar magnet, and every magnet has a north and a south pole. Now, we need to know which materials are actually magnetic. There are only 4 materials that are magnetic. We have iron, we have cobalt, we have nickel, and we have steel. Everything else is not magnetic. So these are our magnetic materials. So if you've got a magnet or something that sticks to a magnet, they have to contain a lot of these materials. So every magnet has a north and a south pole. Now, magnets exert something called a non-contact force. It means they've got an invisible force, an invisible force you can't see, that affects other objects. So in this case, if I had a piece of cobalt, nickel, steel and iron and a big magnet like that in the middle, they would get attracted by this invisible force. And we need to know what that invisible force actually looks like. And that's what we call our magnetic field. Now, just remember, a north pole is actually called a north-seeking pole and a south-seeking pole. And that's because if we hung this on a piece of string, it would turn round until it lines up with the magnetic north pole and the magnetic south pole. Now, I'm going to draw some lines onto my magnet. And I'm going to start here with the north and the south, okay? And then I'm going to take a line that goes around like this and a line that goes around like this. Now, there's lots of these lines. I'm going to put another one and I'm going to put another one here. Now, these are what we call magnetic field lines. Now, you need to know in which direction do they come out of the magnet and which direction do they go into the magnet. Now, just remember, with a magnet, the field lines always come out to the north, so you've got to put arrows on them. So, coming out to the north on each of these, and they go into the south. So there would be my arrows like that. So it's coming, the magnetic field comes out to the north and goes into the south. Out to the north and into the south. Now, I could ask you, where does the magnetism come from? Well, all those lines actually meet right here in the center of the magnet, okay? They continue all the way through. I could also ask you, which part of the magnet is the strongest? And the strongest part is here at the poles. So the strongest part is at each pole. Okay? Now, once we know what the magnetic field lines look like, we've then got to think about, well, what happens and can we explain how a magnet behaves when it comes next to another magnet? Okay? So for this, I'm going to draw at the top, again, part of a magnet. This time, I'm just showing one end. Now, I've decided that this end is a north pole and this end is a north pole. Now, we know that when two north poles of a magnet, we push them together, okay, they push each other away, all right? They do something called they repel. Because like poles repel. Now, you could be asked to explain, well, how does that happen? Because there's nothing physically pushing them away because we have these mysterious non-contact forces. So if I actually draw my field lines on my magnet, so I've got that one. And then remember, it's a north pole, so they come out. We can see here that those field lines, okay, and I'm just going to change to another colour. At these points here, where I'm colouring in, those field lines aren't touching, but they're pushing each other away. So they're trying to push the magnet that way and the magnet that way. And that would be exactly the same diagram if it was a south pole on each side, except on a south pole, my arrows would be pointing towards the magnet. Okay, so that's how we explain why two north poles or two south poles, when we push them together, they push each other apart. But how do we explain what happens if we actually have a north and a south pole that come together, north and south? Well, we know then we bring two poles that are opposite, that they attract. But we've got to be able to explain what's happening with this magical non-contact force. Okay, so we've got to draw on our field lines. All right, and this time what we're actually doing is we're showing that we've got some lines that go straight across. So I'm going to put there. Okay, and we've got some that go like that, and they're pulling the magnets together. Okay, and that's a strong attraction. All right, so we've got our north and our south pole there. All right, now the other thing that I could ask you in your exam tomorrow is, okay, well, we've got this magnetic field, all right, and it's there. We know it's there because we've talked about it. There's a bar magnet made out of iron, steel, cobalt, or nickel. What could I do to prove that there is a magnetic field around that magnet, and which side is north and which side is south? Okay, and what I would actually do, and this is what I would do, is I would take lots and lots of plotting compasses, and I would put them around the magnet. I'm not going to draw loads. You put loads of them around the magnet. Okay, and what you would actually find is that the arrows on them, I'm not drawing those very big, the arrows on them would point in the direction of the magnetic field. Okay, so I'm going to draw a few in there. So what I've done there is a magnetic field line going out, going out, going out. It's got an arrow going that way, going in, going in, going in, going round, going round. And because they're pointing in that direction, they would point toward from north to south. That would be our north and that would be our south. So if they ask you about that experiment, just say we can find the direction of or where the magnetic field lines are using plotting compasses. And we can find the direction by looking at the way that they line up onto the magnetic fields. Now, we've talked about here mainly, okay, permanent magnets. So everything we've talked about is a permanent magnet. So when I actually have a bar magnet like this, that's made out of iron, steel, cobalt or nickel, with a north and a south, okay, it's a permanent magnet. That means it's always going to be magnetic, and it's always going to have its magnetic field lines coming out of it. Now, we can actually make materials like, for example, a paper clip here. We can make it magnetic. We can do what's called induced magnetism. And we can get it to be magnetic, because where it is at the moment, it's nowhere near that magnet, so it's not magnetic. But if I bring the magnet in, if I bring the paperclip into the magnetic field like this, okay, suddenly it does become magnetic because we've induced it. It's in the presence of the magnetic field. It's now magnetized. If I take it away and move it back down here, it's no longer in the magnetic field, so it's not magnetic anymore. But if I bring another paperclip nearby, what I actually find is that that paperclip will stick to the first one, okay? Because that's now become magnetic, because it's got induced magnetism. And I can bring another one and put it on. The same thing will happen. So when we've got induced magnetism, we get attraction. Now, these only have a north and a south pole while they're touching each other, okay? As soon as I take them off, they're no longer magnetic. So the one thing that we need to remember is with induced magnetism, they can only attract other materials. They can never repel them, okay? Now, we're going to start to move on to electromagnetism here and how magnetic fields are created when we use current and potential difference, okay? So that's essentially everything about magnets and magnetic fields, okay, with permanent magnets. We're now going to look at what actually happens when we pass, okay, a current through a wire. So here I've got a wire, okay, and I'm just going to draw a circuit because we need to have a permanent circuit. Okay, so I've just got a wire, a straight wire, and I've got a power source here. There's my battery, okay, and that's sending current in this direction from positive to the negative terminal, and it's passing through that wire. Now, when current flows through a wire, we get a magnetic field. Okay, we get induced magnetism. Okay, so it's induced. So as long as the current is flowing in that complete circuit, there's a magnetic field around this wire in some way. Okay, I'm just going to do it like that. Now, there's a way that we can work out what that magnetic field actually looks like. So I'm just going to change my diagram so we can show that. And the easiest way for us to be able to do that is if I actually have a piece of wood like this, or a piece of card, and I've got a hole in the middle of it, and I can actually pass a wire that goes through it. So the wire's gone through there, and I'm going to say that this end is positive, this end is negative, so my current is moving in that direction. Okay? Now, I need to be able to say, how could I work out the direction that the current is flowing in? Now, there's two ways that I can do that. I can either take a whole load of plotting compasses again and put them around it and see which way they line up, or I can use something which is called the right-hand thumb rule, okay? So it's a little bit like putting your thumbs up, okay? All right, so, but I'm going to put my thumb this direction. So the thumb, okay, points from the positive, and I'm going to write it on my thumb there, positive to the negative. So on my diagram, positive to negative, positive is here to negative, I'm going to put my thumb in that direction. Now, when I turn my thumb to look at it, I can see my fingers are pointing in this direction. So on this diagram, I would actually draw some arrows that's going in that direction. So we can see, if we look at it, my arrow there is going the direction of my fingers. So if it was the opposite way around, I put it down like that, it would go the other way around. Okay? So that's the right-hand thumb rule. Now, I could actually ask you, the other question is, well, if there's a magnetic field around this wire because there's a current flowing through it, well, where is the strongest magnetic field and where is the weakest? So the strongest magnetic field is closest to the wire. So it would be here. Okay. Further away, it gets weaker. Okay. So the further away you get, it gets weaker. All right. Now, we know that a magnetic field is created in a wire when we pass a current through it. Whoop-de-doo, what good is that? All right, it's good for a bit of fun and looking at a magnetic field. We then come on to the bit that really is important. All right, we want to harness that knowledge, and this is where we need to think about a solenoid. Okay, So a solenoid is a coil of wire. So I'm going to draw a solenoid for you. Okay, so there's our solenoid, and it would be attached to a power source. Okay, and there's my positive. Okay, now, so a solenoid, and I'll write that down. Let's use that pen. This is a solenoid, and it's a coil of wire. All right. Now, as the current flows through the wire, I'm going to put some arrows on there, it creates a magnetic field. Okay. Now, because the coils of wire are close together, it makes that magnetic field stronger. Okay. It also means that the field lines line up. So the magnetic field lines line up, and that makes it stronger. Now, I could give you a solenoid diagram and say, can you draw for me the magnetic field, okay, that's found in that solenoid? Now, it's just the same as a bar magnet. So we would have some lines coming out of each end, and we would have some going around and back in, just like our bar magnet diagram that we did. Now, the important thing to remember is all about current. So our current is flowing in this direction. So it's flowing from the positive back to the negative. So because it's flowing from the positive back to the negative, the side that is positive becomes a north pole, and the side that is negative becomes a south pole. So when we draw our arrows, they come out of the north and go into the south. Okay, that's how we would draw our magnetic field lines on there. Okay, really key. Now, solenoids are really useful solenoid, okay, in a solar wobbler, and it causes a magnet attached to the thing that moves to go backwards and forwards, backwards and forwards, backwards and forwards. However, I can make my solenoid even more useful by inserting into the center an iron core. And when I insert that iron core, okay, so I'm going to put plus iron core, I create an electromagnet. Okay, and you might have actually done the practical where you have an iron nail, wrap some wires around it. Wrapping the wires around is making a solenoid. You connect it up to your power pack, okay, and you can pick up loads and loads and loads of paper clips. Now, that's all well and good, but it's more useful if we actually work in something like a scrapyard and we've got to pick up some cars that are a bit bumped and bashed and nobody loves anymore, okay, because they've traded them in because they just fancy something new, okay. So there we've got a little car, and here we've got a big 4x4 Chelsea tractor, okay. Don't want them anymore, okay. If I've got a permanent magnet, okay, I can put that onto my car, pick it up, but I can't let go of it again. It's stuck. It's really hard work. But along comes our electromagnet. Okay, I can put my electromagnet on, turn it on, and it picks the car up. I move it somewhere, turn it off, drops it down. Here's a bigger car. Okay, instead of having to have a bigger magnet, okay, I can just change the amount of current flowing through the circuit. I can pick this car up and then put it down somewhere else, okay? Becomes really, really, really useful, okay? So, really key. Now, essentially, that is it for foundation, okay, magnets and electromagnetism. The next parts are for higher tier only, okay? And for higher tier only, and if you're watching for separate sciences, this is good for you as well. It's all about Fleming's left-hand rule, and just see where I've put my sheets. For Fleming's left-hand rule and also the motor effect, okay? So let's just remind ourselves about Fleming's left-hand rule and then how it actually works. So we have our right-hand thumb rule and we've got Fleming's left-hand rule. So there's where I've got my fingers. Okay, your thumb points upwards, your first finger straight out, and your second finger at right angles. So I've got a diagram here that shows what they actually mean. Your thumb represents the movement or the force that causes the movement. Your forefinger represents the magnetic field from north to south. So remember, the north is where your finger joins onto your hand, and the south is the tip of your finger. And then your second finger represents the direction of the current. And again, it's positive where your finger joins the hand, and it's negative at the tip of your finger. Okay, that helps you to orientate your hand when you're actually using it in your exam tomorrow. Now, what I just want to do though is to go through, before we use Fleming's left-hand rule, okay, the motor effect and what actually happens here. So if I take a horseshoe magnet, and what I'm going to do is I'm just going to draw it like this. Okay, and let's say this is a north pole and this is a south pole here. Okay, so we've got a horseshoe magnet, looks a bit like a horseshoe. And if I then actually place into my horseshoe magnet, okay, a coil of wire. Now I'm drawing it like this because that's sort of like it looks like in the diagrams. Now remember, there's lots and lots of these going round. I'm only going to draw a few. It's a coil. It's not just one line. Okay, so there's lots of them. Okay, going round. All right. If I place a coil of wire, okay, into a magnet, and I then pass a current through it. So my current, okay, we've got a circuit here. I'm just going to draw it really small. There's my battery. Going back, so that's my positive. So the current is going that way. When I pass the current through the coil of wire, okay, I induce a magnetic field. Now, here I've got a magnetic field. So I'm going to do my magnetic field. Remember, my magnetic field, I'm going to do it as dotted lines, even though they're full lines, go north to south. So they're going north to south, like that, across the whole thing. So I've got a permanent magnetic field there. Okay, it's always turned on. And I've suddenly switched on my coil of wire, and it's now got a magnetic field. Now, can you see at this end here that as the current's going through these wires, that becomes a north and this becomes a south? Well, look what we've got. Two norths together, two souths together. They're going to repel each other. Okay, so that's going to cause our coil, because at the minute it's lying like that, straight across, it's going to cause it to rotate and go like this. So it's going to rotate upwards and downwards. Now, this is where Fleming's left-hand rule comes in, because I could ask you, which direction does it move in? So let's get our hand ready, okay? So I'm going to start off by taking my finger, okay, and I'm going to write on it here, NS plus minus. Okay, so I'm going to take my finger north to south. Okay, so that's pointing in the right direction, north to south. We can see that. However, my current finger, oh, it's pointing in the wrong direction. Okay, so I'm looking, just move my hand out, I'm looking at this side here only. So I've got to have my finger pointing that way, plus, minus, north, south. You can't write on your fingers tomorrow, you get chucked out the exam, so don't do it. Okay, naughty, naughty. So we can see north to south, current positive to negative, because the negative is going to come around this way, and my thumb is pointing downwards. So that means that this is going to go down, and this end will go up. And that is using Fleming's left-hand rule. Okay, so literally, ladies and gentlemen, okay, for the trilogy students, that is about it. That's all we need for magnets, electromagnets, waves, and forces. Okay, so we're just going to have a quick 30-second, 2-minute break. Okay, while I just change my sheets, and then we'll go through the separate science stuff for waves and magnets and electromagnetism. Just a reminder that space physics, I did space physics the other day. Okay, so space physics for separates is online now. So 2 mins.
If you've got any questions, Year 11, please feel free to send them still through to our Twitter. While Mr. Cattrall is going through the separates only content, I'm staying on live on the Twitter account. So any questions that you ask, I will answer as we go through. Okay? Please make sure that you get them into us now, because we won't be able to answer them once we've gone offline, because we'll both be going home. So please get them in and ask us now as we go through. If you go to Horizon, you have a booster tomorrow morning at 8:15, and it's an extended booster until 8:55. Okay, so we're normally 30 minutes, we have you for 40 minutes. And then we're going to go into the theatre, an exam talk from me, and then it'll be into the exam ready for 9:30 start. So make sure you are in school. I don't tell you this, oh, I can revise better on my own at home, or I didn't know what time it was. That's not an excuse. You need to be in, you need to be with us. We're standing by tomorrow morning, ready to go through some last minute things with you. Okay, so just like Mr. Cattrall said, this is for separate students only. If you go to another school, you may call it triple science. I know some schools call it that still. If you go to Horizon and you are not in set 1, this bit now is not relevant for you, okay? What I am going to do is I'm going to stop the stream and start a new one, because I know then it gives the stream for trilogy students time to upload while the separate one is going at the same time. To know people ask if we can upload it, and we can't until we've finished. So I'm going to stop this stream now. I'll start a new one up, and that will be for set 1 students only. So we'll see you shortly.